Hello. This presentation is designed to take away some of the mystery from units of measurement in the world of engineering technology. How we measure things is just as important as what we measure, because if you don't understand the method of measurement, then how can you possibly measure things accurately or understand measurements made by other people? Now, first of all, there are countless systems of measurement in the world used by different people for different purposes. However, in the world of engineering, there are two main systems. There is the SI, which stands for Système International. That's a newer system originating in France. It's now becoming more and more popular across the world. It's also sometimes called the MKS system, and that is an abbreviation for meters, kilograms, and seconds. Now, this is an important concept because every system of measurement is based on, primarily, its chosen units for distance, mass, and time. The SI uses the meter for distance, the kilogram for mass, and the second for time. And every other unit in the system is actually a mathematical combination of those three units. The other system you need to know about is the British imperial system, also sometimes called the American system, and its abbreviation is FPS for foot, pound, and second, which are its chosen measurements for distance, mass, and time, respectively. This system tends to be most popular in any country that used to be part of the British Empire. That includes the United States, Canada, the United Kingdom, and many other English-speaking nations, although most, aside from the United States, tend to be shifting more and more towards the SI. So let's take a closer look at some of the units used by these two systems. So we'll start with mass, which I give the very vague definition of the amount of stuff in something. Stuff in this case is matter, and this isn't a very good scientific or scientifically correct definition, but this presentation isn't designed for theoretical physics, so this is what I'm going to go with for now. The key thing is that since mass is the amount of matter in an object, it won't change depending on the location of that object. So wherever I move the object, it will still have the same amount of matter contained within it. The SI unit for mass is the kilogram, which is also the mass of 1,000 cubic centimeters of water at 4 degrees Celsius. The imperial unit is the pound, or pound mass. Another unit that you might see in the imperial system for mass is the slug, which isn't used very often, but you might see it at some point. And one slug is equal to 32.174 pounds mass. And in case you want to convert between the two systems, it's a good thing to note that 1 kilogram is equal to pretty close to 2.2 pounds mass. So the next quantity we'll talk about is force, which is closely related to mass in many ways. The SI unit for force is called the Newton, and 1 Newton is defined as the force required to bring an object with a mass of 1 kilogram up to a rate of acceleration of 1 meter per second squared. If you remember Newton's second law, force equals mass times acceleration, so a unit of force should be made out of a unit of mass times a unit of acceleration. Therefore, a Newton is 1 kilogram times a meter per second squared. Remember, SI is the MKS system, so every unit in it is made of meters, kilograms, and seconds. And the Newton is one very good example. You can see kilograms, meters, and seconds as part of it. For the imperial system, the unit of force is unfortunately the pound, or the pound force. This is unfortunate because it causes a lot of confusion between force and mass, both of which are measured in pounds, which forces us to say pounds force and pounds mass to specify which one we're using at a given time. The pound force is actually defined using the pound mass. 1 pound force should be the force of gravity that is exerted on an object with a mass of 1 pound mass on Earth at sea level. Another unit of force you may never see, but I'm putting it in because of its similarity to the Newton, is the poundal. This is an imperial unit, and 1 poundal is the force required to bring an object with a mass of 1 slug to a rate of acceleration of 1 foot per second squared. So I mention this because it's similar to the Newton in that it is also a mass times a unit of acceleration. So it works well with Newton's second law, unlike the pound force. Now, another very important measurement is weight, which we sometimes think of as being the same as mass. However, weight is actually defined using force. The weight of an object is defined as the amount of gravitational force acting on it. So the units we use for weight should be the same as for force. For example, if I stand on a scale in my bathroom and it says I weigh 190 pounds, is it pounds mass or pounds force? The answer is it should be pounds force. So how would I measure my mass if I wanted to? Well, to measure mass directly, you shouldn't use a spring scale. Instead, you should use an equal arm balance scale. Then if I put an object with a mass that I know is equal to, say, 100 kilograms on one side, and then I sit on the other side, then if the scale is balanced, I know my mass is the same as the 100 kilograms. This measurement doesn't change depending on the force of gravity. So I can do this measurement on Earth or on the Moon or anywhere else and should get the same result. However, you can also calculate mass mathematically using your weight, but you need one more piece of information to do that, which is the gravitational acceleration at the place where you happen to be standing. This slide shows the calculation you would make using imperial units, which is probably harder than with SI units. Start with Newton's second law, force equals mass times acceleration. So weight, or force of gravity, equals mass times gravitational acceleration, which is abbreviated as g. So mass would equal force of gravity divided by g. In this case, I used the weight I measured as 190 pounds force. So divided by g, g equals 32.174 feet per second squared, which is standard acceleration due to gravity at sea level on Earth. But you can't do this calculation yet because the units aren't right. If you divide pounds force by feet per second squared, the result won't be in units anyone will understand. They will be in pounds force per foot per second squared. But we want the result to be in pounds mass because that's something that's easier to understand. So first, you have to convert pounds force to pounds mass times feet per second squared. And pounds mass times feet per second squared is actually another measure of force that is more useful because it comes from a mass times an acceleration as per Newton's second law. So it's more like Newtons or poundals. So you need to use this unit conversion here to change pounds force to pounds mass times feet per second squared. And to do that, multiply 190 by 32.174. That gives 6,113 pounds mass feet per second squared. So just to be extra clear, this is what happened when I converted 190 pounds force. So instead of 190 pounds force, we've got this number here in pounds mass feet per second squared. So then that number is divided by 32.174 feet per second squared because that was the value of g. And the result is 190 pounds mass. So what just happened here? It may seem a little strange that we started out with a weight of 190 pounds force, did all this weird calculation, and came up with an answer that was the same, only in pounds mass instead of pounds force. Well, the problem is that they won't always be the same. The only reason this was the same this time is because I assumed I measured my weight in a place where g equals exactly 32.174 feet per second squared. So let's try measuring it somewhere where g equals exactly 32 feet per second squared instead, like on the top of a mountain where gravity just is a little bit less than at sea level. So this time, we'll assume I still measured my weight as being 190 pounds force. So I put that in for force of gravity equals my mass times 32 feet per second squared, which is g. Mass comes out to be 6,113 pounds mass feet per second squared divided by 32 feet per second squared, which leaves an answer of 191 pounds mass. So this time my mass came out a little higher than it did before. Why is it higher? Well, if you think about it, pounds mass and pounds force are defined to be the same when g equals 32.174, because that's the standard gravitational acceleration. And if g is less than 32.174, my mass will be a bit more than my weight. But if g is more than 32.174, like on Jupiter or somewhere else with a lot of gravity, if I could stand on Jupiter anyway, then my weight would be more than my mass in that case. In the SI, everything is a bit simpler, partly because it uses kilograms for mass and newtons for weight, which makes it easier to keep them separate rather than using the same word for both things. So if I happen to measure my mass as 86 kilograms, all I need to do is multiply this by the gravitational acceleration measured in meters per second squared. In this case, 86 kilograms times 9.8 meters per second squared is 842.8 newtons. And that's the answer. There's no need for an extra step of converting the units of force because the newton is defined to be a kilogram times a meter per second squared. So that takes care of one of the more confusing things in measurement, which is the difference between mass and weight, and combine that with the difference between pounds force and pounds mass. But let's move on to some other types of measurements using both the SI and the British imperial systems. So here are a few other compound units. A compound unit is simply a unit that is a combination of other units being multiplied and divided together. And all are actually a combination of units for length, mass, and time. We've already seen one such unit, which is the Newton, which is kilograms times meters divided by seconds squared. So other ones include the units for work and energy, which are actually the same. They're measured the same way. And there's power, which is a rate of work being done, and pressure and density. Those are all important units in engineering. So starting with energy, the SI unit for energy is the joule, and 1 joule is equal to the amount of work you would do on an object by exerting a force of 1 newton to it across a distance of 1 meter. Work is just the net change in energy over an interval of time, so we actually use the same unit to measure both, joules. The imperial system uses the foot-pound, or foot-pound force to be more technical. The imperial system uses the foot-pound, or foot-pound force to be more specific, which you can see is similar to the joule. But joule is a newton times a meter, then both are actually a unit of force times a unit of distance. There just isn't a special name for the foot-pound, the way a newton meter is called a joule. And other units for energy that you may run into are BTUs and calories. Both of these are defined in different ways based on the energy required to raise the temperature of water by a certain amount. And even though these definitions are very different from the definitions for the joule and the foot-pound, you can still convert between all of these things easily because they all measure the same thing, energy. Now, power is just the rate of work being done. So all we need to do is take a unit used for work and divide it by the unit for time. So in SI, the unit is called the watt, and a watt is a joule per second. So 1 watt is equal to 1 joule divided by 1 second. In the imperial system, the usual unit is horsepower. Now, you could measure this thing in foot-pounds per second, and that would actually make a lot of sense because it would be the same way as I just said with the watt. You take the unit we were just using for energy or work and divide that by seconds, and you would get foot-pounds per second. And that is one way you can measure power in the imperial system. And the horsepower is actually defined using that. 1 horsepower is equal to exactly, it's defined to be equal to exactly 550 foot-pounds per second. So other units you might run into, the foot-pound per second, like I said, or also BTUs per second. Since BTU is a measurement of energy, BTUs per second would be a unit for power. Another important quantity is pressure, and it's very important in thermodynamics, particularly in studying engines, fluid power systems, a lot of different kinds of power generation. Pressure is actually defined as being a force exerted spread out across an area. In SI, the main unit for pressure is the Pascal, which is 1 Newton per square meter. So for example, if you had a weight of 100 newtons and placed it on the floor and measured the area of the floor that the weight was sitting on as being exactly 1 meter, then the pressure would be 100 pascals. 100 newtons divided by 1 meter would give 100 pascals. Another unit we see very often for measuring pressure is bars, which comes from the Pascal. The reason for using bars to measure pressure is that it is a nice round number that's very close to the atmospheric pressure on the surface of Earth, or barometric pressure, same thing. So engineers like using the bar to measure pressure because it gives a good idea of how much more or how much less the pressure is in, say, a cylinder or another type of thermodynamic system versus its surroundings. Surroundings you would assume to have a pressure very close to 1 bar because that would be atmospheric pressure. So if you want a number even closer, though, to the normal atmospheric pressure, you could use the unit called atmospheres, which is exactly 101,325 pascals, which is very close to the 100,000 pascals that make up a bar. In the imperial system, the unit for pressure is pounds per square inch, or PSI. And just remember that it's pounds force divided by square inches, which again is like the Pascal. It's a force divided by an area. And I'll mention 1 or 2 more measurements here with compound units. Density is an important one, and it's defined as the mass per unit volume. So it's measured in kilograms per meters cubed in SI. There's no special word for it. Or it could be measured in pounds mass per foot cubed in imperial. The symbol for density is the Greek letter rho, which is important to note because it looks like a P. You can see it here. But so don't get it confused with symbols for pressure or power because that's not a P, it's a rho. And that comes from the Greek alphabet. Now another very similar unit or measurement is specific volume, which is volume of a material per unit mass. Now in the language of thermodynamics, anything specific, anything with the word specific in front of it, is almost always measured per unit mass. So specific volume is volume divided by mass. Specific energy is actually energy divided by mass as well. I'm not going to get into that, but it's a good thing to remember that anything specific is divided by mass. Now you might also notice that means specific volume is the same thing as density, but it's turned upside down. So specific volume is volume over mass, while density was mass over volume. The symbol for specific volume is a lowercase v, which is another thing to keep in mind. And usually you'll see it written in italics, like it is here, or in cursive, just to separate it from net volume, which is the uppercase V. That would be the total volume that an object has, whereas the smaller one is specific volume. And we measure that in meters cubed per kilogram, or feet cubed per pound mass, because that's the same as the units up here, but flipped upside down.